Chemistry time.
Hadley, you let it down. Do it again. Cut. Okay, do it again.
Chemistry time.
Okay, good. We're going to talk about colligative properties of solutions. Colligative properties of solutions. Just looking at the word colligative, looks kind of like Colgate. That's not what it's actually related to. But can you? This might be kind of a stretch, but can you guess what English word colligative is related? Well, colligative is an English word, but what other more common word colligative is related to? Just as a guess. It's related to collect. This is the it's related to the word for collect, and this means either the properties a solution has because of the collection of particles that it has within it. Properties a solution has due to the amount of solute, not the nature of solute. So for instance, if I have a tub of red Kool-Aid, right, is the red color a colligative property? No, because the red color is due to the nature of the solute. Whatever, some red dye is making it red. Whereas the colligative properties are those that are because of how much there is, not because of what they are.
Like how sweet it is?
That would probably be a factor of how much sugar is in it, which would be due to the nature of sugar, right? We couldn't dissolve salt by the same amount and have it be just as sweet. But something like, we're going to get to 3 of these things, but something like freezing point depression, where the freezing point gets lower, right? It doesn't matter what we dissolve in water, but if we dissolve anything in water at all, the freezing point gets lower. Why might that be important? When would we want the freezing point to be lower? I can see it outside right now why we might want the freezing point to be lower. Where might we want the freezing point to be lower of water?
Of water?
Yeah. Where might we want the water to be a liquid instead of a solid?
In this one?
No. No. You're thinking the other way around. It's making the freezing point lower, meaning it'll take a colder temperature to make it freeze. So where might we want it to be colder before it freezes? Like, it doesn't reduce the temperature, it just makes it so...
Can you give us like a little hint of what you're...
Yeah. So where might we want there to be... There already is water. We don't want there to be solid water there. We want there to be liquid water instead. Outside. Right now. Because it's dangerous.
Right now?
Yeah. Where would it
On
be
the
dangerous?
streets.
Yes, exactly. So things like ice melt, and when they spray the roads with the liquid de-icer, all it's doing is they're adding some solution. It doesn't even matter what the solution is. Anything dissolved in the water will make it so the freezing point is lower. So if we just spread salt, for instance, on your sidewalk, it makes it so the water can't freeze until it gets to a lower temperature. Think about like the Titanic. When the Titanic sank, it was well below freezing. It was like 18 degrees outside, but the water was still liquid because there's salt dissolved in that water, right? You see what I mean?
Yeah.
That's a colligative property. It doesn't matter what kind of salt is dissolved. It could be sodium chloride. What they use on the roads usually is calcium chloride. It could be anything, right? It could be alcohol. Anything dissolved in the water will make the freezing point lower. There are 3 of these that we're going to talk about. There are more, but there are 3 that we're going to talk about today. They are vapor pressure lowering, so let's write these down. Vapor pressure lowering, we're just going to list them first. Vapor pressure lowering. Boiling point elevation. And freezing point depression. This is not the first time in the last couple days that the word depression has come up in here. We talked about the cone of depression in earthquakes. Remember the cone of depression? Yeah. It's where the well draws down.
Mm-hmm. It's kind of in its name.
Yeah. It lowers. That's what depression actually means, right? When we talk about something like clinical depression or bipolar depression in a person, it's a lowering of the mood. That's understood.
You're not happy.
Yeah, you're low.
An all-time low. You ever heard that song?
That's a band even. Is it a song too? Anyway, so vapor pressure lowering just means that, and we don't really do math with this, so we're kind of going to leave it alone a little bit. But the vapor pressure is how much the particles are exerting, how much pressure the particles are exerting on a container as they go from a liquid to a a liquid to a gas, which is a vapor. So we can just put the vapor pressure decreases as solute is added. Let's define vapor pressure real quick. Your book says, in Chapter 12, you learn that vapor pressure is the pressure exerted in a closed container by liquid particles that have escaped the liquid surface and entered the gaseous state. So that's all. Is that as gases are evaporating inside of a substance, the particles exert some pressure on it. Called the vapor pressure. There's a neat little diagram you can look at if you're watching online. You can look at this on Google. Just type in vapor pressure and you can see a diagram. But in your book, there's a picture on page 499 called vapor pressure lowering. Like I said, we don't do math with this one. I'm not sure why your book doesn't include math for vapor pressure lowering, but it does include math for the following two, and we're going to talk about both of these right now. So the boiling point elevation, just based on what it sounds, right? We're not going to really define this one because we don't. We're going to define it mathematically instead. But just looking at what is going to happen, what do you think is going to occur? Just based on the name.
The boiling point. Sorry we were interrupted. Back to our video.
Back to our scheduled program. Anyway, what's going to happen to the boiling point and when?
Wait, okay. So
Yeah, what's going to happen to the boiling point?
It's going to increase?
The boiling point is going to increase when what?
When the elevation increases.
No, elevation means it's going to raise. When boiling point is going to increase when we add more solute, right? So basically, conceptually, which is going to have a higher boiling point? A gallon of water that you've dissolved 1 tablespoon of salt in, or a gallon of water you've dissolved a cup of salt in? A cup of salt, right? The more solute there is, the higher the boiling point gets. And we write it this way. Delta T sub B, can you guess what that means?
Temperature sub volume? B.
B.
Boiling point.
Yeah, boiling point. And delta is?
You
know it. Delta is?
A Greek letter.
Yes. Yes. Come on, you know it. Delta is?
Elevation.
Change in. So we're calculating change in boiling point.
Oh.
Change in boiling point. Boy, I'm disappointed. The change in boiling point, right, how much it's been elevated, the change in boiling point equals something called the Van 't Hoff factor, which we're going to talk about in a second.
I.
Cursive, lowercase I,
Well,
times
we do this in math.
K sub B times M. You didn't do this in math. That's an imaginary number. This is a completely different thing from that. So the change in boiling point is the Van 't Hoff factor, and we're going to talk about that in a second, times K sub B, which is the boiling point elevation constant. Listen to me. The boiling point elevation constant is true always for a particular solvent. So you look up the solvent, either on the internet or on page 500, and it will tell you K sub B for that substance. Look right now. On page 500, there's a whole table of K sub B's for each of these substances. It gives you water, benzene, carbon tetrachloride, ethanol, and chloroform. The one we're going to use the most is probably what?
Probably water.
Probably water. So we look up the K sub B on here, given in degrees Celsius per mole. And then lowercase m here, speaking of mole, is molar. Where delta T sub B is, what did we say?
Is change in boiling point.
Change in boiling point is going to go up or down.
It's going to probably go up.
Yep, it's always going to be positive for this. I already said, is the Van, spelled this way. I've never seen anything spelled like this before. I'm sure it's named after a person. Van 't Hoff factor. And this, I guess it's a little bit complicated, but all it is how many different particles will be in that solution. So for covalent solutes, what's an example of a covalent solute? God bless you.
Thank you. An example of a covalent solute,
Yeah.
is that what you said?
Yes, solute. What's something that we can dissolve in water, for instance, that'll be...
Salt or sugar?
Not salt. Salt is ionic, so sugar, but sugar is. So for a covalent solvent, I is equal to 1, almost always. For ionic solute, I is equal to the number of different types of ions. So for example, sodium chloride, how many different types of ions are there in sodium chloride?
2.
2, sodium and chlorine. What about calcium chloride?
Still 2. Wait, 3.
3, because CaCl2. And that's why, and this becomes very important, that's why, in fact, that's one of the reasons they use calcium chloride on the roads, is because for a given amount of calcium chloride, it has 3 times the change in boiling point, right? Or freezing point, as we'll come to find out. And then K sub B, as we said, K sub B is boiling point, what we call molal boiling point elevation constant. And this is given in degrees Celsius per molal. And M, lowercase m, is molality. And remember, molality is a measure of concentration. M is a measure of concentration. Okay? Freezing point depression works very similarly. Let's do an example of one of these real quick, though, so just so that we're on the same page. What is the boiling point elevation of a 0.625 molal aqueous solution of any non-volatile, non-electrolyte solute? So what it means by non-volatile is that we can do this equation with it. And what it means by non-electrolyte is that the Van 't Hoff factor is going to be 1. So we have a 0.625 molal aqueous solution. What's aqueous solution mean?
Aqueous can be dissolved by water.
Dissolved in water. So we're going to write our equation first. Delta T sub B equals I KB. Yep, we're just doing an example. Delta T sub B equals I KB. Yeah. And we're trying to find delta T sub B, so we don't need to manipulate. What's the Van 't Hoff factor? Well, I just said it's non-electrolyte, so it's covalent, and it's non-volatile, which means we can use this equation. So what's the Van 't Hoff factor? 1. Easy. And Van 't Hoff factor is the unit list. And then K sub B, where can we find the K sub B for water?
It's 1.86.
No.
0?
You're looking at freezing ones probably. It's different. Molal boiling point constants are given on page 500. 0.521. 0.5, is it 21 or 12? 0.512 degrees Celsius per molal, and then the molality is 0.625 molal. Do you notice it didn't even say what stuff it is? It says any solvent. It doesn't matter. This could be sugar, it could be ether, it could be isopropyl alcohol, it could be anything as long as it's covalent. And so all we have to do is multiply 1 times this times this. The math is really easy, right? It might be a little bit conceptually difficult to understand and what do we put in where, but the math is super easy. So just type in your little calculator, 0.512 times 0.625, and that is it. .32. 0.32, what is our answer going to be in? Look at what our units are.
Degrees Celsius.
Just degrees Celsius. And so, instead, what's the normal boiling point of water?
Isn't it like 100?
Yeah, 100. So delta T sub B, delta T sub B is that. So now our T sub B, our boiling point, equals 100 degrees Celsius plus 0.32 degrees Celsius. So 100.32 degrees Celsius. So like I said, the math is in no way difficult. It's just figuring out where to get the numbers from. Okay? Questions about any of that?
No.
Let's move on to freezing point depression. Freezing point depression. So what do you think is going to happen here, conceptually?
We're going to find the freezing point.
We're going to find the new freezing point. But what's going to happen to the freezing point if we add solute to it?
It's going to
it's going to decrease. So the more solute we add, the lower the freezing point is going to get. Freezing point depression is given as delta T sub F equals I K sub F M. It's the same exact thing, except we're going to have a different value for K sub F, which is now called the freezing point depression constant, molal freezing point depression constant. And delta T sub F is now change in freezing point. And what is this going to be, positive or negative? Is the freezing point going to go up or down?
It's going to go down.
Down. So our freezing point is going to be, our answer is going to be negative. Our answer we'll actually get is going to be positive, but we will subtract that number from whatever the freezing point used to be. Now we're going to do another practice problem here real quick, and then we'll be done unless you have questions. The practice problem reads, what is the freezing point of a 0.40 molal solution of sucrose in ethanol? What should I do first?
Write out the equation.
And what is the equation, Hadley?
Delta T of F.
Delta T sub F.
Delta T sub F equals, what is it that I called it?
Van 't Hoff factor.
Van 't Hoff factor. K sub F, N.
N. Okay. My question reads, what is the freezing point of a 0.40 molal solution of sucrose in ethanol? So what am I trying to find here? I'm on page 503, on number 46. I'm only doing the freezing point. So I'm trying to find the new freezing point. So in my equation, what am I trying to find? The delta T sub F, right? Okay, so delta T sub F equals, what's the Van 't Hoff factor if it's glucose? Sucrose. Well, sucrose is covalent, so what's the Van 't Hoff factor? 1. And what's K sub F for ethanol?
1.99.
Yep, I'm sorry, hold on. That might be true. It is true. 1.99 degrees Celsius per mole. And the molality it gave me was 0.40 molal. Delta T sub F equals
0 mole.
Yeah. This is like a mixed drink. Sucrose dissolved in ethanol. You can't have that yet. Like a margarita, basically it's this. There's some water too though.
1.796.
1.796?
Yep.
Let's just, well, okay,
I
1.80.
didn't mean to say 1.
What?
It's just 0.796.
0.8. Thanks. 0.8 what?
Degrees Celsius.
Degrees Celsius. Is that the answer?
Yep.
Nope.
Nope, it is not, because now we have to add it to freezing. Subtract it from the freezing point.
And what was the freezing point of ethanol?
32.
Nope.
Oh.
How do we know the freezing point of ethanol?
Oh, it's here. It's negative 114.1.
So T sub F equals negative 114.1 degrees Celsius minus 0.8 degrees Celsius gives us a new T sub F of negative 114.9 degrees Celsius. So given what we know now, is it good to use, should we use sugar as a road de-icer?
No.
Probably not, because it only has a Van 't Hoff factor of 1, you see? So if we have something like, let's think of oh, here we go. This would be a good one. It doesn't dissolve in water, I don't think, but Fe2O3 has a Van 't Hoff factor. It doesn't dissolve. But if it did, it would have a Van 't Hoff factor of 5, right? That would be good. So basically, instead of this being 0.8, it would be 4.0, right? It's 5 times as good because the Van 't Hoff factor is 5 times as much. So really, when we're looking for colligative properties of solutions, we get the greatest change with things that have the largest number of ions in solution.
Okay.
Do you have questions about any of this?
I don't think so.
Do you?